Section 7.5, proportions in triangles. Theorem 7.4, side splitter theorem. If a line is parallel to one side of a triangle, here DE is parallel to BC, and intersects the other two sides, then it divides those two sides proportionally. And that's what DE does. It is parallel to a third side and intersects side AB and AC. This is different than the mid-segment theorem, which would tell me that point D and E are midpoints of the two sides. Then that would make that segment parallel to this third side, but also half as long. That doesn't occur here because D and E are not the midpoints of the two sides of the triangle. But this theorem states that I can set up a proportion of the two sides, which would mean I have AD over DB, and that's equal to AE over EC. I also could set up the proportion in this manner, where I have the bottom over the top, which would be DB over AD, which equals EC over AE. If I would use the cross product property, I would get AD times EC, AD times EC, and DB times AE, and DB times AE. The problem with the side splitter theorem is it does work for the sides of the triangle, but does not work for the bases of the triangle, the two parallel sides. Does not work for the parallel sides. To find the measures of the parallel sides, I need to go back to the fact that these are two similar triangles. I know that they're similar by the AA theorem. A is in both triangles, the small one and the large one. Therefore, by reflexive property, they are congruent to themselves. And also, since these are parallel, I can get corresponding angles congruent here and here. Therefore, I can use the AA theorem to prove the triangle similar. And if that position is true, then I need to find the measure of the two bases. And therefore, to do that, I need to use a scale factor. And recall, a scale factor is AD over AB, or AE over AC, or DE over BC. These ratios cannot be used to solve for the base of DE and BC. So here, let's take a look at an example. They want us to solve for X and Y. I'm going to tell you the first thing that I would do is always find a scale factor. But let's try the theorem, which is the side splitter theorem. So this is the side splitter. Therefore, I know I have QR, which is X, over RS, which is 10, and QU, which is 6, over UT, which is 18. Therefore, when I use the cross product, I'm going to get 18x is equal to 60. Divide by 18 on both sides, and I'm going to get x equal to 10 thirds. I cannot use this ratio to find the value of y in this problem compared to 4. I need to find a scale factor. Recall, a scale factor is a ratio of two known sides. So here it would be QU over QT. So my scale factor would be 6, which is the small triangle. And again, I can use AA theorem to prove these two triangles, the small and the large, are similar. 6 over 6 and 18 add up to be the length of QT, which is 24. That gives me, when I simplify, a scale factor that is going to be 1/4. Now, I can find y using the scale factor and see that that is different than our value here, which, if I simplified this, would be 1/3. So to do that, I get 1/4 equal to, and I want small, 6 over 24 large, so I'm going to go small over y, which is 4 over y. Therefore, I get y equal to 16. I could have used this scale factor to solve this problem. And if I did, this is what it would look like. 1/4 equals small, which is x, over large, which is x plus 10. Then I would cross product rule, get 1 times x plus 10, which is the distributive property. I still get x plus 10, equal to 4x. Subtract x on both sides, I get 10 equal to 3x. And again, dividing by 3, I get x equals 10/3. Therefore, I recommend not using the side splitter theorem. You can see it works, but don't get caught in the trap that you solve the bases in that fashion. I still need a scale factor, so I always go right at the scale factor. One more bit of information about the side splitter theorem before we look at the next example. When I set up the ratio, I have to go top over bottom or bottom over top, or if it was laid on its side, left over right or right over left. I cannot set the ratio up in a diagonal fashion, 6 over 10 or 10 over 6, or x over 18 and 18 over x. That won't work. And I used that same type of proportion or ratio on my first example, which I had top over bottom or bottom over top. I cannot use the diagonal ratio to solve the problem. The side splitter theorem doesn't work that way. Our next example, again, I always like to use the scale factor, but since this is the side splitter, I'll use that as an example and then go right on to the scale factor. So here's side splitter. And that works because I have a segment's parallel to a third segment of a triangle and intersects the other two sides. When that happens, I can set up top over bottom or bottom over top. I'm going to go top over bottom. 3x over x plus 4 equals 8 over 4. But I'm going to simplify that to be 2 over 1. Cross product gives me 3x equal to, distributing the 2 through the entire expression, 2x plus 8. Then I subtract 2 on both sides. I get x equal to 8. Therefore, these sides would be 8 plus 4, which is 12, and 8 times 3, which would be 24. But to solve for y, I need to find a scale factor. That scale factor will be a ratio of 2 known sides of the small and large triangle. That would be 8 for the small triangle. I'm going to go small over large. And for the large triangle, 12. And when I simplify my scale factor, when I divide the top and bottom by 4, I'm going to get 2/3. Then I set up my proportion, 2/3 is equal to small y over large 16. Cross product rule, I get 3y equal to 32. And when I divide by 3, y is equal to 32 over 3, or 10 2/3. Let's verify this with the side splitter theorem. I can use 2/3, and my lengths would be small, which would be 3x, over large, which I would add these together, and I would get 4x plus 4. Product rule of proportions gives me 9x equals, when I use the distributive property here, I'm going to get 8x plus 8. Subtract 8x on both sides, I'm going to get x equal to 8. Notice I get the same answer using the side splitter and the scale factor for the sides of the triangle that is intersected by that parallel side. Therefore, I always use the scale factor, but we verified that with the side splitter. Corollary to the theorem 7.4, I have if three parallel lines intersect two transversals, then the segments intercepted on the transversal are proportional. In other words, this is very similar to the side splitter theorem. If I would increase the length of my lines, which is possible, they would form a triangle, and I would get something very similar to the side splitter theorem. In other words, I can set up a proportion of the sides or the intersected segments by the parallel lines, which would be A over B, and I went top over bottom, so it's going to be C over D, or bottom over top, B over A equals D over C. And again, if I use the cross product, I'd have B times C, A times D. And again, as the side splitter information tells us, I cannot go diagonally using the ratios to set up a proportion. That will not give us a valid response to our examples. Here I want to solve for the variable in each diagram. I'm given three parallel lines intersected by two transversals. Therefore, it cuts off those segments proportionally. So I'm going to go left over right and set up the theorem from the previous page. So it's going to be 3 over 8 is equal to x over 5. And when I use the cross product rule, I get 8x equal to 15, and x is equal to 15/8. Again, I could have went left over right, or 8 over 3 and 5 over x, but I cannot go diagonally. Use the figure to complete the proportion. Here I want to use the known ratio and follow the pattern to complete the unknown ratio. Here I'm given A over B, top over bottom. Therefore, that will be D over E. Next, I have C over B, bottom over top, which will then give me F over E. Next, I have C over the sum of the two top segments, AB. Therefore, I'm having F over the sum of the two top segments, which is E plus D. Here I have D over A. D over A. That's valid in the side splitter and in this theorem, because as long as I don't go diagonally, I can go left over right, top over bottom, bottom over top, or right over left. It doesn't matter as long as I don't go diagonally. Therefore, I have D over A, and I have a B, so therefore that will be E over D, which is the left over right, left over right. My last theorem, 7.5, triangle angle bisector theorem. If a ray bisects an angle of a triangle, here AD bisects angle CAB, then it divides the opposite sides into two segments, here DC and DB, that are proportional to the other two sides of the triangle. Therefore, I can set up a proportion of the two segments that are created by that angle bisector and the other two sides of this triangle, which would give me CD over AC and DB over BA. Or I could also say AC over CD and AB over BD. And if I use the cross product rule, I get AC times BD, AC times BD, CD times AB, CD times AB. Here we have an example. We want to solve for the variable in each diagram. Here I'm given a triangle with an angle bisector, and from the previous theorem, I know that this bisector divides these two segments in proportion to the other two sides of the triangle. I'm going to set up my proportion, x over 12, the segment adjacent to its side of the triangle, is equal to 14 over 16. which is easier to simplify this ratio. So let's do that. X over 12 is equal to, divide both by 2 here, I get 7 over 8. Cross product rule, I get 8x is equal to 84. Divide both sides by 8, I get 84 over 8. Divide the top and bottom by 2 to simplify. That's going to give me 21 over 2, or 10.5. Our next example, again, I have an angle bisector, therefore it divides those two segments in proportion to the sides of the triangle. I can go with x plus 4 over x equal to 18 over 10. Again, it's simpler to simplify that fraction, so x plus 4 over x equals, dividing both by 2, I get 9/5. Cross product rule, distribute with the 5, I'm going to get 5x plus 20 equals 9x. Subtract 5x on both sides, I get 20 equal to 4x, or x is equal to 5. And if I needed to know the lengths of the segments, this segment would be 5, and this segment would be 5 plus 4, which is 9. Again, I want to find the value of x in this diagram. I'm given a segment that's parallel to another segment in this diagram, therefore I can get corresponding angles congruent, and of course A is reflexive to itself, therefore the triangles are similar by the AA similarity postulate. With that, I could find a scale factor and find the unknown side. So let's go with 6 over 8, which is the length of my long side, which is AB. Scale factor, the ratio of two known sides, small, which is 6, over large, which is 8. Simplifying, I get 3 over 4. And when I use the same idea, I'm going to have small over large, which is 3 over 4, equal to small over large, which is 16. Therefore, 4x is equal to 48, and x is equal to 12. This procedure can be used to find the parallel segments of these two triangles. But since these two segments are parallel from the side splitter theorem, I can use the segments created by that parallel side to set up a proportion. Therefore, if this is x, this would be 16 minus x for the length of CE. Therefore, if I go top over bottom and top over bottom, when I simplify that fraction to make it easier, it gives me 3 over 1. Cross product gives me x, and distribute this expression with 3 gives me 48 minus 3x. That gives me 4x when I add 3x to both sides, equal to 48. Divide by 4, I get x equal to 12. I get the same solution for x, and also I can find 16 minus x, which is 16 minus 12, which gives me the length of CE, which is 4. I could have done that on both of these values, but this is the only one that I could use to find ED and CB. Our last example, we're given a triangle JCF and triangle JBE. We're also given 3 parallel segments cut off by 2 transversals. And I'm given angle bisector, which is segment JG, JH, and JI. Therefore, I can use these proportions to find the missing ratio on the opposite sides. Remember, what we want to do is use the 3 theorems that are in this section and follow the pattern that is used. Here I have AB over AC. Therefore, that's going to give me, since I'm using GI, GI is here, so AB over AC, and the bottom is GI, this top part must be GH. Next, I have EF. EF over JE. So the small over the entire part here, JE. So that will give me, I know, BC over JB. Next, I have JA over BC. And now I have HI. Therefore, that's going to give me JG over HI. Here I have JC over CI. Now I'm using the angle bisector theorem. So JC over CI gives me GF over the segment that the angle bisector creates, which is FI. Next I have JB, which is here, over HB, another angle bisector theorem, which means here I have HE. That tells me that the other segment must be JE.